All right, let's talk about the vital signs of electronics. Just like a doctor checks your heartbeat and your blood pressure to see how you're doing, a technician uses quantitative measurements to see what's really going on inside a piece of equipment. This is how we find the problems and keep everything running the way it's supposed to.
So that really is the big question in electronics, isn't it? Electricity is totally invisible. You can't see it, you can't hear it. So how in the world do you diagnose a problem you can't even perceive? Well, the answer is you measure it. Think of these measurements as our eyes, letting us peek inside the circuits to see exactly what's going right and, more importantly, what's going wrong.
Okay, here's our game plan. First, we'll get the big picture on why we even bother with all this. Then we're going to dive into the three big ones: impedance, power, and frequency. After we nail those down, we'll do a quick-fire recap of the key terms and then hit you with some practice questions to see what stuck. Sound good? Let's get into it.
All right, section 1. So, why these three specific measurements? Well, it's because together they give us a complete health checkup for a circuit. Impedance tells us how much the circuit is fighting against the flow of energy. Power tells us how much energy is actually flowing. And frequency, that tells us how fast it's all happening. They're basically the three pillars of performance in electronics.
And this is the bottom line, right? We're not just collecting random numbers for fun. These measurements tell us, point blank, if a part is doing its job. If the manufacturer's spec sheet says a resistor should be at 50 ohms and you measure 500, well, you've just found your culprit. It's all about hands-on, practical problem solving.
Okay, let's start with our first big topic, impedance. In the simplest terms, it's just the total opposition that a circuit puts up against an alternating current. And to measure it with real precision, we use this super clever tool called a bridge circuit. The best way to picture it, think of one of those old-timey balancing scales, but for electricity.
The concept here is actually pretty genius. On one side of this bridge, you've got known, calibrated values that you can adjust. On the other side, you put your unknown component, the thing you're trying to measure. You then tweak the known side until that little detector in the middle reads exactly 0. Once it's balanced, boom. The value you dialed in on the known side is the exact value of your mystery component. It's simple, elegant, and incredibly accurate.
Now, this isn't a one-size-fits-all deal. Just like you wouldn't use the same scale to weigh a bowling ball and a feather, you need the right bridge for the right job. The Wheatstone bridge is kind of your everyday workhorse for general resistance. But for those super tiny, very low resistance values, you gotta grab a Kelvin bridge. Measuring a capacitor, that's a job for the sharing bridge. And for an inductor, you'll be choosing between a Hay or a Maxwell bridge.
Okay, this is a classic exam question, so listen up. When do you use a Hay bridge and when do you use a Maxwell bridge? They both measure inductors, so what gives? It all comes down to something called the Q factor, or quality factor. Just think of Q as a rating of how good the inductor is. A high Q inductor is very efficient with very little energy loss. For that, you use a Hay bridge. A low Q inductor is, well, it's a bit leaky with higher energy loss. For that, you need the Maxwell bridge. Easy way to remember? High Q, Hay, low Q, Maxwell.
So we've just talked about how to measure the opposition to energy flow. Now let's flip that around and look at how we measure the flow itself. It's time to talk about power. This is all about gauging just how much energy is being used or moved around in a circuit, and we measure it in watts.
The most direct way to get a power reading is with a watt meter, like the one you see here. The basic idea is that inside you have these different coils of wire. As power flows through, they create magnetic fields that interact and literally push a needle on a dial. The more power, the stronger the push, and the higher the needle goes. It's pretty straightforward.
But what if you're dealing with a ton of power? I mean, like the output of a huge radio transmitter. A regular watt meter might not be able to handle it. For the really big jobs, we need a different and way more accurate method, and that's where the calorimeter comes in. The principle is brilliant. Just convert all that electrical energy into heat and then measure the heat.
And this is a perfect example of how that works. In this adiabatic calorimeter, you basically dump all the power into a load that's sitting in a sealed container of water. All you do is measure the water temperature, apply the power for a very specific amount of time, and then measure the temperature again. Based on how much the temperature changed, how much water you have, and how long you ran the power, you can calculate the wattage with incredible precision.
All right, we've covered resistance and we've covered power. Let's move on to our third key measurement, frequency. This is all about speed. It could be the physical speed of a spinning motor or the speed of an electrical signal cycles like in a radio wave. Getting the frequency right is absolutely crucial for almost everything.
So, to understand one of the coolest ways we measure frequency, I want you to just use your imagination for a second. Picture a fan spinning so fast that the blades are just a complete and total blur.
Okay, now imagine you're in a dark room with that blurry fan, and you've got a strobe light. A light that you can make flash on and off, and you can control exactly how fast it flashes. As you adjust the flashing rate of your strobe light, you'll hit a point where the flashes perfectly match the rotation of the fan blades. And when that happens, something amazing occurs. The fan will look like it's completely frozen, standing perfectly still. You've just synchronized your light to the fan's frequency. And the tool that does this is called a stroboscope.
And I have to share this safety warning. It comes straight out of the manual. It says, "The illusion of stopped motion is very convincing. Do not attempt to touch the moving equipment." And it makes sense, right? It might look totally still, but it is absolutely moving at full speed. It's a pretty good reminder that our tools can definitely trick our senses.
Phew, okay, that was a lot of information. To make sure all this stuff really sticks in your head for your exam, let's do a super fast, rapid-fire recap of the most important terms. Ready? Let's go.
First up, impedance bridge. That's our balancing scale for electricity, right? We use it to measure an unknown by balancing it against a known.
Next, the Kelvin bridge. This is your high-precision tool, the specialist you call in when you need to accurately measure really, really low resistances.
Then we have the calorimeter. Remember the water tank? This is the super accurate way to measure high power by turning it all into heat and measuring the temperature change.
And finally, the stroboscope. That's the cool tool with the flashing light that lets you freeze motion to measure the speed of something that's spinning.
Excellent work. Now that those key terms are fresh in your mind, let's really put your knowledge to the test with a few practice questions taken straight from the material.
Okay, first question for you. Kelvin bridges are well suited for what type of measurements? Go ahead and think about it for a second.
And the answer is small values of resistances. Exactly. They're the precision tool for when a standard bridge just isn't sensitive enough.
Question number 2. Power measurements that are performed with calorimeters are based on what 3 variables? Think back to that water experiment.
And the answer is temperature, mass, and time. That's right, you measure the temperature change of a known mass over a specific amount of time.
All right, last one, and this one's a little bit of a curveball. What is the primary measurement application for tuning forks?
The answer is they're used to monitor fixed motor speeds. Yeah, they work kind of like a low-tech stroboscope, giving you a fixed reference to check if a motor is holding a steady, correct speed.
So, there you have it. You now have this powerful toolkit for seeing into the invisible world of electronics. You know how to measure the opposition, the flow, and the speed. You're equipped to diagnose problems and verify performance. The only real question left is, what are you going to measure first?